She's talking about bridging gaps between observations and theory. So, Marie, go ahead.
Okay, great. Sorry, forgot to unmute myself even after a year from working from home. So I will talk about bridging the gaps between observations and theory with an emphasis on the gaps when it comes to the chemistry in AGB outflows. AGB outflows are very rich astrochemical laboratories. Close to 100 different types of molecules have been detected so far, as well as some 15 types of dust grains. The type of chemistry is determined by the elemental carbon to oxygen ratio of the star itself. And we have carbon-rich outflows, oxygen-rich outflows, and there's also the intermediate S-type chemistry. Throughout the outflow, chemistry and dynamics are closely coupled, and we can distinguish three main regions, each characterized by their own chemical and dynamical processes. In the inner winds, the chemistry is taken out of equilibrium because of shocks caused by stellar pulsations. Then a bit further out, dust is able to condense from the gas phase, and it's here that the outflow is launched. In fact, it's the micro-scale chemical process of dust formation that launches the macro-scale outflow. And then finally, in the outer winds, the density is low enough for interstellar UV radiation to penetrate this region and cause a very rich photochemistry. So there's different types of chemistry throughout the outflow, and this diversity is caused by the large gradients in density and temperature. So we go all the way from some 10 to the 13 particles per cubic centimeter in inner winds to some 10 particles per cubic centimeter where the outflow merges with the ISM and also pollutes the ISM. And in temperature, we go from a few thousand Kelvin to some 10 Kelvin. And this is precisely what makes AGB outflows unique. Other astrochemical labs, such as dark clouds, do not show such a wide variety. So it's interesting, but it's also a bit more complicated. Now, when we look at chemical models of AGB outflows, there's different types for different types of chemistry. Inner wind chemical models deal mostly with the non-equilibrium aspect of chemistry up to the point of dust formation. Chemical kinetics models are geared towards the gas phase photochemistry in the outer winds. And then recently, myself and collaborators implemented dust gas chemistry in such a chemical kinetics network. So this extends the chemical validity of the model from the outer wind into the dust interaction zone. But a model that's valid from the stellar surface all the way to where it merges with the ISM is not possible as of yet. And one of the major bottlenecks is dust formation. Now, this is also a simplified view of the AGB outflow. Reality is much more complex. Here you can see the postcard of the ALMA large program Atomium. So it's CO around oxygen-rich AGB stars. And well, none of them are spherically symmetric. Some are a bit more than others, but yeah, it's not spherically symmetric. And these asymmetries are thought to be caused by binary interactions. So it's definitely a complex and connected problem, and such a complex problem requires an ambitious goal. In an ideal world, I would like to have a full hydrochemical model and couple it with radiative transfer, and we can throw in some magnetic fields for the aficionados as well. But before we can get there, we need to solve the issues we have in our current, mostly one-dimensional chemical models. And for that, we need laboratory astrophysics. Lab astrophysics will help us with retrieving chemistry from the observations, as well as with the chemical modeling of the observations. Let's start with retrieval from observations. The most straightforward example is light identification. We have terabytes upon terabytes of observations, and in almost all spectra, we still have some unidentified lines. This means that we are missing out on already available information. Now, if we were to talk to some laboratory chemists, spectroscopists, and some quantum chemists as well, we could identify those lines and identify new species. And the group led by Verniciaro has proven that this is quite a successful formula for the dark cloud TMC1. You might have noticed it on arXiv. Plenty of new species have been discovered because they have the data, they have the lab, and they have the quantum chemists. So a fruitful way forward. To retrieve abundances from observations, you need radiative transfer. And in order to run a radiative transfer code, you need collisional rates. And collisional rates matter. That's something that Thaisa Danilovic found out when modeling H2S around oxygen-rich outflow. So first of all, the H2S rates don't exist. They're actually scaled H2O rates. And yeah, H2S, H2O, they're similar, but they're also different molecules with different electronic structures. And then also there's different sets of rates for H2O depending on the temperature regime you're in. But in an outflow, we have all these temperature regimes. So which one do you choose? And turns out that the choice of collisional rates really affects your results, as you can see here. So both the initial abundance as well as the envelope size. Now, I already mentioned this issue at a previous conference, a laboratory astrophysics one. And this brought us into contact with researchers in Tunisia, and soon we will have collisional rates for H2S. So talking about your problems sometimes helps. Now let's switch from retrieval from observations to chemical modeling of observations. And let's talk about dust formation, the main bottleneck. You can study dust formation using a laboratory approach, and this is done by the NanoCosmos team, who have built an experimental setup that is able to mimic dust formation in carbon-rich outflows. And it's doing so while modeling it under conditions relevant for AGB outflows. And that's exactly what we need: experiments based on AGB conditions and not dark clouds or protoplanetary disks. And by making the environment more realistic in their experiment, so by adding acetylene, they found out that this has quite the impact on the dust grains that you form. So there's more, and both things like the amount and the size of the dust grains. So definitely check out their recent paper. Now, you can also take a more observational and theoretical approach regarding to dust formation. I'm going to switch to oxygen-rich outflows because there the problem is even a bit more complex since we don't know what the seed particles are for oxygen-rich dust. Aluminium oxides appear to be good candidates based on observations, but when Jels Boulanger developed his hydrodynamical model, and he included dust nucleation as well, he found out that you can make aluminium oxide clusters, but only if the monomer is present. So you can't start out with just aluminium and oxygen floating around, which is the case in the outflow. So are there perhaps cluster formation pathways missing, or are the reaction rates involving the production of the monomers not accurate, or both? That's also possible. So there's still lots of work that needs to be done, both observationally and theoretically. Now, inaccurate rates are not an issue limited to this model alone. In fact, at the heart of every chemical kinetics model, we have a reaction network. So that's the list of all the reactions that you include together with the reaction rates and the temperature dependence of these. But if you want to make a complete network, you will have to include inaccurate rates because, well, not all rates, reactions have been studied in the lab, or you can't even study them all in the lab because you have health and safety regulations. Some things are quite toxic or explosive, you can't even measure them in the lab. This pie chart shows you the accuracy of the reaction rates included in the RAID 12 database. So there's about 6,400 reactions in that database, and most of them have quite a good accuracy. So the error is smaller than 50% for more than a quarter of them. The majority, more than 50%, have a factor of 2, so not great, but quite a large chunk has a factor of 10 as an error, and that's definitely something to improve. But as chemical modelers, we should be aware of the assumptions of limitations and then proceed with caution. And while we proceed with caution, we can keep track of all the reactions with like large inaccuracies and pass them along to a friendly chemist who can then provide us with more accurate rates, but also we can provide them with an impetus for experimental research. These laboratory setups are quite laborious and expensive. You need to have a reason before you start. I'm part of the aerosol consortium, where we collaborate with chemists at the University of Leeds, and Niklas West has improved upon the reaction rate of CH plus formaldehyde, so both the rate itself as well as its temperature dependency. Now, I plugged that back into our chemical model, and it doesn't really have a lot of influence for an AGB outflow, a bit more so for dark clouds, but yeah. So this shows us that it's not only improving the accuracy of the rate that matters, it also depends on the reaction, because of all the 6,400 reactions, of course, not all of them are going to be as important. So as you continue your chemical modeling, please keep an eye out for inaccurate important rates. Another way to improve your chemical model is to add new chemistry. And as I mentioned before, I developed a dust gas chemical kinetics model, and I was able to do so because I'm collaborating with Catherine Walsh, who is an expert in chemical modeling of protoplanetary disks. And while dust gas chemistry was new to us, it's not new at all to protoplanetary disk and dark cloud chemical modelers. It's quite standard chemistry that's included there. We found that dust gas chemistry can have a significant impact on the composition of the outflow. So gas phase species can be accreted onto the dust and form an ice mantle. The depletion level depends on the outflow density as well as the drift velocity between dust and gas, because these two parameters govern the amount of collisions. Temperature of the dust also plays a large role because it shouldn't be too warm for an ice mantle. And then finally, also the composition of the outflow matters. Here I show you the results for a very dense oxygen-rich outflow with the coldest dust, so you're maximizing the depletion here. The dashed lines are for gas phase chemistry only. Dust gas is the solid lines. And as you can see here, H2O is readily depleted onto the dust, and that's because it has a large binding energy. Other species such as SO or CO2 don't particularly care, but the impact can be large. Regarding to the discussion on Monday, we also found that the depletion of gas phase species depends on the grain size distribution that we assume in our model. Now, this gas phase depletion level can be retrieved from observations. You do need to observe quite a wide range of molecular lines and probe the entire outflow, but you can retrieve the depletion level, and then that can be related back to the grain size distribution using our chemical models. So this is useful to the AGB community, but also to the ISM community, because AGB dust is an important starting point of the dust evolution in the ISM. And these different curves show you the the effect of different grain size distributions. Now, if you add new chemistry, you also add new problems. The binding energies that play such a large role have mostly been measured on water ice, because that's the case in dark clouds, and most of the experiments have been geared towards dark clouds so far. But the binding energy depends on the surface to which the molecule binds, and the binding energy can increase if the dust grain is bare. And that's the case in AGB outflows. Like, we form them, and well, they start out naked. And Amy Wilson-Holm-Hogg, in her Masters of Chemistry project, she performed electronic structure calculations, and she found that the SO binding energy goes from 1800 Kelvin onto ice, all the way to 15,000 Kelvin on bare silicate dust. And then you're on the right, you see the abundance profile of SO in an oxygen-rich dense outflow, and how it is affected by implementing this switch. So if the dust grain is barely covered, we use 50,000 Kelvin, and then we switch back to the old value. The SO abundance profile shifts from this Gaussian profile to a more shell-like shape. And these shell shapes of
2 minutes
SO,
left.
thanks. The shell-like shapes of SO around oxygen-rich dense outflows have been observed before. So this could be a way to produce them. But in the meantime, Tom Miller and I have been working on a simple model that takes the effect of companion UV photons into account, because we know that the companion is there, we see its effect on the structure, but if the companion is a star, it will also emit UV radiation. And this will start off the rich photochemistry already in the inner rings, so not just in the outer rings, already in the inner rings. And for dense oxygen-rich outflows, we would see again that this shell-like shape reappears. So different processes give similar results. And in order to differentiate between the processes, we will need a comprehensive view on the chemistry throughout the outflow. So not just study one molecule, but study as many molecules as possible, because different species will react differently. To conclude, AGB outflows are rich astrochemical laboratories, and their chemical richness is definitely a challenge to our modeling efforts, but it's also an opportunity for collaborations within astrochemistry and within laboratory astrophysics. We need input for observations, retrieval, and modeling, and we can provide them with a guide to laboratory research. These interactions are essential to close the gaps between our current chemical and otherwise models and the observations. It's only by doing so that we can get a better understanding of the outflow and its contribution to the ISM. Thank you.
Okay, thank you very much,